Hi everybody. In this video we're going to work on exercise 2E, which has to do with Newton's second and third laws. This is a very common problem on the AP test, and you'll see a lot of multiple choice questions on this particular situation. I will read it. Two blocks are being pushed across a surface with an external force F, as shown in the figure at the right. The mass m2 of block 2 is greater than the mass m1 of block 1. The blocks begin at rest. The surface is smooth enough that the frictional forces between the surface and the block can be neglected. So it's always really important to read the problem, read it like a lawyer. You're going to see a lot of little catchphrases in there, such as the blocks begin at rest, such as frictional forces can be neglected, things like that. So you want to always take the time to read the question and think about it before you start to do anything. Okay, so the first question in part A says that the dots represent the two blocks. Those are kind of like the centers of mass of those two blocks. So that's the center of mass for the first block. And of course, this is the center of mass for block 2. So I'll just put numbers by there. It says to draw free body diagrams showing and labeling the forces, not the components, exerted on each block. Draw the relative lengths of all the vectors to reflect the relative magnitudes of all the forces. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So let's begin with dot 1 for mass 1, which is right here. And there is a force acting on that. I'm just going to call it FA for applied force. Okay? I'll make it kind of long. So that's the person pushing on the block. Okay? Now, what are the other forces that act on block 1? Okay, the one that's probably the easiest to come up with would of course be the weight. We'll call that the force of gravity. That's the Earth pulling on block 1. And then because the block is on a level surface, there's also a normal force which is equal and opposite to that. So when I draw that second vector for the normal force, I want to make sure that it's the same length. I can put tick marks on there to show that. I'm not too worried about the specific number of blocks that I'm using, but I just have to make sure that they are the same. Now, here is the tricky part. Newton's third law says that when block 1 pushes on block 2, which it has to, then block 2 has to push back on block 1. So there's one more force I need to add here. This is going to be block 2 pushing backwards on block 1. That's going to be a reaction force. Okay? So if 1 pushes on 2, 2 pushes back on 1. And I'm also going to use common sense, and I'm going to not make that backwards force be as big as the applied force, because that would mean that the block might move backward, accelerate backwards, or at least be canceled out, which wouldn't make any sense. So this force is going to be the force of 2 on 1. It is not equal to the applied force. In fact, it is less, and your drawing has to show that. So this is the tricky part. So you've got 4 forces then that act on block 1. Okay? The verticals will cancel, the horizontals do not. Now, for block 2, here's the easy thing you can do, is you can immediately say that if you had the force of 2 on 1 pushing back this way, that means that there must be an equal and opposite force of 1 on 2, which is pushing block 2 forwards. These are the action and reaction forces. Okay? And again, it doesn't matter what you call them, but they are a pair. Therefore, they must be equal and opposite, and they act on 2 different objects. Okay, 2 different objects. In terms of the other forces that act on block 2, of course we're going to have the weight, the gravitational force, and the normal force. I want my picture to be accurate somewhat, so I'm going to make the weight greater. Okay? And the normal force also must be greater. So I'm going to extend those all the way. So you can tell that they are not the same size as the gravitational force and the normal force. So now I need to do some tick marks like this to show that those are equal and opposite. Okay? And then lastly, is there any force that points to the left on block 2? And I go back up and it says that frictional forces can be neglected. So my conclusion is no. And there wouldn't be any other force. What else would push block 2 backwards? Nothing. Don't think that the inertia of block 2 is a force. Don't think that just because block 2 has mass, that's going to be a force pushing it back. That's not actually it's not a force. That's the inertia. And that will come into play in the argument underneath. So there are only 3 forces shown on this. That's it. Okay? There's no force going to the left on block 2. Very important. Okay. So, oh, and by the way, should probably say this, that it's very tempting to say that the normal force and the gravitational force might be action and reaction. Because they're equal and opposite, it's tempting. You want to say that, right? But that's not true. The big hint is that both of these forces act on the same thing. And whenever forces act on the same thing, they cannot be action and reaction. Same thing applies to block 2. Don't be fooled. Don't think that Fg and Fn are action and reaction. Okay, they are not. I'm not going to get into the full discussion of that, but each of those forces does have a reaction partner, but it involves something that's outside this system. So the gravitational forces involve the Earth. I'm not sketching the Earth. The normal force involves the table or the surface, and I'm not going to sketch that. So I am not sketching the reaction forces to these 4, the 2 Fgs and the 2 Fns. I'm not going to sketch those reactions. There's no need to. All right, part B, it says, derive the magnitude of the acceleration of block 2. Express your answers in terms of m1, m2, g, and f. Okay, and they mean here Fa. That's the applied force. So they get us started here. They say that the sum of the forces in the x direction is equal to m times the acceleration in the x direction. Everybody, that's just a fancy way of saying F net in the x direction. So sometimes you see this sigma. That sigma means sum. That's what net means. It's the sum of the forces. And when you put the x here, that means that you're just doing things in the x direction. Okay. We don't really need to write the equations in the y direction here because we know that the forces cancel. There's really not much to learn there. So we're going to focus on the x direction here. All right, the next thing you would want to do here, it says derive, right? The magnitude of the acceleration is that we want to get at that acceleration. So now what we want to do is identify our system of objects, okay? So this system is going to be both objects, okay? It's going to be both things. In other words, this is the system. And so when I think about that and I apply Newton's second law, I look at what forces act from the outside world on that system. The only force that acts from the outside world is this push, right? This is your Fa. That's the person, because the person is not in the system, right? Not in the system. So anything the person does to those blocks is outside. So for that reason, I'm going to write Fa here. That's the only force that's kind of a net external force on this system. And then the mass that I have for my system, again, if you look at the picture, is going to be m1 plus m2. Okay? And my acceleration is my acceleration. Okay? I think I made a little bit of a jump here because I think I jumped the gun. And I noticed that this next prompt says here, it reminds me to do the mass, and so really probably I should have put these masses down here. It doesn't matter. This is just meant to show you the thought process, right? So to kind of summarize here, in this first step, they want you to recognize that FA is the external force. That's the important idea there. In the second step, they want you to recognize that it's the total mass that counts. Okay. All right, so those are important conceptual steps. Then it says the acceleration of the system. So the acceleration, we just basically rearrange. Okay, and I can divide both sides by m1 plus m2. And so that would be an expression for the acceleration of the entire system. Right? It's the applied force divided by the total mass. And the very last thing here is to say, hey, everybody, remember, you were supposed to derive the acceleration for block 2, right? That was the whole goal. But if you think about it, logic tells you that both of these objects have to accelerate together because they're connected. So whatever the acceleration for one is, it's got to be equal to the acceleration for 2, and that's got to be equal to the acceleration of the system in the x direction. So the last step that you're doing is you're really just kind of recognizing that that's true, and so your acceleration for block 2 is going to be equal to the acceleration of the whole system in the x direction. And so you're going to have this same expression. It seems kind of redundant, right? You're really just saying the same thing that you have here, but you're recognizing that those accelerations are in fact the same. Okay? Now, we'll do one more thing that might help you. I'm going to put some numbers on this. Students always like that, and it's a good thing. So let's pretend that the person applies a force of 120 newtons. Let's pretend that the mass of object 1 is equal to 10 kgs. Let's pretend that the mass of object 2 is equal to 30 kgs. Okay? And so first of all, let's find the acceleration of the system in the x direction. Right? That's going to be equal to FA over m1 plus m2. And so I've got 120 newtons divided by 10 plus 30 kgs. And that's going to give me, of course, 120 divided by 40, which is 3 meters per second squared in the positive x direction. So the whole system accelerates at that rate. Okay? So everybody, that also means that the acceleration of 1 and the acceleration of 2 have to be the same thing. So you've really got like 3 different accelerations here for your effort. Okay? Everything is equal to that. Now, the one other thing I'll throw in here is, what if they said find the force of 1 on 2? Huh. Let's look at that. That would be this force. Find the force of 1 on 2. Okay. Well, you might say, well, that's easy. That's the force of 2 on 1. It is. However, we don't know that. And you might say, well, that's just the applied force of 120. But you would be wrong, because we said that that force is not equal to this one, right? So how do you figure this out? How do you get this? How do you find this force? And here's the key. For object 2, you know that it accelerates at 3 meters per second squared. Okay? And you know that the mass of object 2, we said was, 30 kgs. And so it should be totally possible to find the force that causes that acceleration. Maybe you can do it in your head right now. You've got 30 kgs accelerating at 3 meters per second squared. What force causes that? And of course the answer is 90 newtons. Let's show that with the math. So to find that, the force of 1 on 2 is going to be equal to the mass of object 2 times the acceleration of object 2. And hopefully you've been following along here, because we've just said that you can take your 30 kgs and multiply by your 3 meters per second squared, and that's going to give you 90 newtons. Okay? So what's interesting about that is if you go back, right, and you say, okay, that's 90, right? This is 90. And you say, all right, well, if that's 90, then this must be like negative 90, right? Because it's going the other way. And then you say, well, the applied force was positive 120 newtons. And this makes sense, right? At least it's reasonable that my 120 is a larger force than my 90. And so the 120 is going to win. By the way, subtract those two, right? So if you do F net on 1, let's see if that works. The net force on 1 is 120 minus 90. Mass of 1, we said, was 10. Let's just see if everything works. 120 minus 90, that would be 30. And that gives us the same acceleration that we figured out in the beginning. Wow. So we knew that already, but it's a great way to check your answer and make sure you're doing stuff right. Okay? So yeah, that's how we do these problems. Now, you guys can apply this in the next side. You can go to, what is it, side 2. Okay? You can try it out. I want you to do the same type of reasoning, the same logic, all that stuff. Then you can do a math problem with this. And again, you can use 10, you can use 30. And then for this block, let's make it 20. These are all in kgs. Okay? And again, you can make the push. Let's keep it 120. I think it's good for you to see that. So they're going to ask you some conceptual questions here, and then you have to figure out some things. I will tell you the answers for the acceleration of the system. The acceleration should be plus 2 meters per second squared. And let's see, the force on 2 is going to be equal to 60 newtons. And I would challenge you to prove that to yourself. This would be the force of 1 on 2. I would also challenge you to find the force of 3 on 1. See if you can do that. Okay? And I'll tell you what the answer to that is. That's going to be 8. Wait, let me think about this for a second. 80 newtons. 3 on 1. Let me just do some mental math on that. Yeah, so that should be 80 newtons. So you confirm that, guys, okay? So you can take it from here and here, try them out, have fun. Hopefully you got the idea here. So Newton's third law, very important. It's more than just a conceptual thing. It helps you to understand that forces occur in pairs when objects interact with each other. Okay, so you've got two objects interacting, you've got to have a force pair there, and that helps you to answer questions about the system. See you later.